Hello, in the next few minutes I'm going to show you how a mathematician thinks. The idea behind this is so that you have a model from which you can work. And then you will be able to make discoveries, do critical thinking, and find math very easy. So let's begin. To begin, we need some kind of incentive. So on the left-hand side, I'm showing you how multiplication is done in the conventional way, where we start with the 5 and we continue multiplying across. However, if we wanted to add another digit, we'd have to do the whole multiplication over again. And so what the mathematician is trying to do is to figure out how he can do that problem easier, faster, and more accurately. And we will now go through the process to show how that is done. To begin, we must start with the bases. On the upper left-hand side, we see that we are adding 4 numbers and getting the answer 4936. What we discover is if we use multiplication, we can write that in a simpler fashion. We don't have to write down 4, 1, 2, 3, 4, just one of them, and then use basically our knowledge of multiplication to get the answer. In the middle, upper middle, we see that when we multiply by 10, we just put a 0 after the number. If we multiply by 100, we put 2 zeros after the number. Our next item, the commutative property, says no matter what order we do our multiplication in, we get the same answer. And then we look at number structure. 1, 2, 3, 4 can be written as 100 plus 200 plus 30 plus 6. And we've shown we can replace those hundreds with zeros. Now 134 could also be written as 130 plus 4. And 130 could be written as 123 minus 4. This is important for us to understand later on what we're doing. And then finally we have the distributive property, where we show that we multiply 2 sums times each other. We multiply first by the first letter, and then we multiply by the second letter and add the results. We show this with numbers because people feel much more comfortable when they see it with numbers. Now, first we show 1, 2, 3, 4 multiplied by 1, 2, 3, 4. I put the zeros in reds there because usually I leave them out because they just happen to be a distraction. But basically, the second line, the 37020, we obtain by multiplying by 30. And so we put the 0 for the 30, and then we continue multiplying by 3. However, in the next one over, when we multiply 1, 2, 3, 4 by 1, 2, 3, 4, we multiply by the 1,000 first, and then the 200, and then the 30, and then the 4. And we see that we have the same set of numbers, except they're upside down. And we get the same answer. Well, that shouldn't surprise us, because the commutative property says that no matter what order we do addition or multiplication in, we should get the same answer. Now, we move over one step, and what we do is we now concatenate a 5 to the 1, 2, 3, 4. And if we're using the same process we did in the middle step just previously, all we would have to do is multiply the 1, 2, 3, 4 by 5 and shift it over by one place, because now everything else has been multiplied by 10. And now we just add the results. So it just took us one multiplication in addition to get the results. But if we hadn't made use of the previous results, we'd have had to do all those multiplications all over again and get the same answer. So what we begin to see is that by questioning the way we've done things in the past and change the order, we can't argue with the fact that we're staying within the set of rules, but we just happen to be multiplying from the left-hand side instead of the right-hand side. And this makes us think about things a little bit differently, because what we notice is that the digits to the furthest right, when they're multiplied, have less impact on the beginning of the number. So now let's continue and see what else happens. So when we're solving a complicated problem, we do a simpler problem first. And now we're getting to the real problem. What we would like to do is we would like to multiply 1, 2, 3, 4, 5 times 1, 2, 3, 4, 6. And what we remember before, that 1, 2, 3, 4 squared was equal to 1, 5, 2, 2, 7, 5, 6. Now, what we're basically making use of is the distributive property, showing that A and C are the same value, and B is 6 and D is 5. So what we do is, our first multiplication was the 1, 2, 3, 4 squared. The second one was the 5 times the 1, 2, 3, 4, 5 times the 1, 2, 3, 4, and the second one was 6 times 1, 2, 3, 4, sort of a cross multiplication. And the last one is 5 times 6. We add them up, and we get the answer. So we didn't have to do all of those multiplications over again. We only had to do 3 multiplications, which took about 10 digits. But if we tried to do it the way we did before, we would find that it would take 25 digits. Now, one of the things that we like to do in mathematics is to check our answers. So I've reversed the project and multiplied 1, 2, 3, 4, 5, and subtract 5, which gives us the 1, 2, 3, 4 back again, and then subtracted the 6, and used the distributive property again, remembering a negative number times a negative number is a positive number, and I got back my original answer. So this is one thing that's very important. You want to check consistency. Do your work in different ways. So mathematicians at first seem to be doing extra work, but that extra work is to understand what's going on. So you may ask, why are we doing it this way? Well, let's take an example. If we're multiplying 2 irrational numbers, numbers that go on forever, we don't start from the right-hand side. We start somewhere in the middle usually. Okay, and I'm doing it in the conventional way, just to show you before, but normally we'd multiply by the 1 first and not the 5. But we now get our answer as 2.3712, etc., and we're wondering how many places is it good to, since there are an infinite number of numbers that follow those dots. So we just increase the 5th digit by 1, and we now make use of the multiplication from the first set, do our distributive property, and we now see that the answer was good to 4 places, that we get an error in the 5th place. So again, it only takes 11 digits to check that answer out, as opposed to 25 digits if we had actually multiplied the 17782 and the 13336. So this, as we can see, is powerful. This is just one example that I've used to illustrate the idea of multiplying in the different direction and why this makes sense in terms of the way we look at numbers. I used multiplication as an example because it's something that we're all familiar with, and it goes contrary to the way you learn things. And in fact, I tried to illustrate through a proof process that it made more sense to do it this way, where you start from the left rather than from the right, particularly when we think about how we interpret and look at numbers. So mathematics is more than just learning how to play with numbers. It's a thought process. And so it's a way of sharpening or practicing that thought process on things that we know the answer to. And as I showed you before, I had a problem which basically said, how can I make use of earlier work without repeating it? So necessity is what leads to discovery. So, and usually that happens by just playing around. And it's not just to mathematics that necessity, it's anything that we do in terms of trying to find out what would happen if we did something a little bit different. So mathematics is about the easy way to get the correct answer. So I showed you that extending what we learned made it easier to do other problems. Okay, when motivation and excitement are enhanced, we become interested in doing this. We need a foundation to do more sophisticated thinking. That's why in the second chart I showed you 5 of the basic things in arithmetic we learned, and now gave a reason why we should learn those. Okay, and this particular problem shows how I went about to solve a problem. You didn't see all the sweat that I went through in doing this because I summarized it in this presentation. And the secret to almost anything in terms of problem is recognizing a pattern and taking advantage of that pattern. And though this is a mathematical example, the thought process we went through would be the same kind of thought process that lawyers, writers, poets, scientists, and many others go through in order to find out how to solve a problem and eventually become leaders in their field. So hopefully from this lesson that it will give you the incentive encouragement to try to think outside the box and discover things for yourself and learn to challenge, because that's what I did when I solved this problem. I learned to challenge the way we did things normally in multiplication and found by doing a little bit differently it gave me more insight. Thank you for your attention.